Exam will be at 7:15 or 7:30. What did we agree on?
Both are okay.
We have to decide one of them. So 7:15 or 7:30? I prefer 7:15. What about you? Let me see. Why Mu'ad 7:30? You have something before? Commitment? Or what? Oh, please speak up.
والله عندي لاب دكتور فكلمة تأخر اختبار كلمة صعبة.
متى خلص اللاب يا معاذ؟ Feel free شباب to discuss.
أنا أقرأ 44 يخلص.
5 يعني يقول.
تقريبا.
خلاص 7:30.
ممتاز.
Others please. Okay, so we'll start at 7:30 at Rome 2011. I'll announce that. I already reserved, the room for the exam. Okay, so I'll announce this. Okay, I'll proceed with the material.
Doctor, what about the duration of the exam?
1 hour and 15 minutes. 1 hour and 20. Okay?
Yes, okay, thank you.
It will be reasonable, I mean. The exam is similar, structure-wise, similar to the first exam. However, the material is different, Now, it's more advanced, so if you have studied well, you will be able to do well, Similar to the first major. And it's a chance, please, as I told some of you who didn't do well in major 1 to do better in major 2. And the ones who did very well in major 1, they can continue, doing, very well in major 2 and the final exam. Okay, good. So let us proceed with the material, and then I'll listen to your questions, please. You'll have roughly 1 hour, 1 hour and 10 minutes. It's okay. I'll have office hour tomorrow, please, from 2 to 3:15. You are welcome to come and ask questions, or you send questions over Teams. Some of you, they did already, and I'm answering them, over Teams. Both are okay. I mean, you are welcome in either case. Okay. So let us proceed. Are we sharing the same screen?
Yes.
And as I go over the material, I discuss the quizzes, because some they asked for discussing the quizzes, so I promised them to do that, in the help session, to discuss. So the recording is on. Yeah, perfect. Just to make sure. So we start with the signal space, for major 2, you remember, namely the GS procedure, which leads to the signal space. So the GS procedure is a must, and you will see it the second major and even in the final exam. There is no secret about this, so you have to be ready for this. Now, my experience from the quiz and the assignment, usually, the first step is easy. Everyone gets it. In here, the graphical subtraction. Some of you did confusions, in the quiz. So please do it carefully. This is the place where common mistakes take place, in the GS procedure. Otherwise, straightforward. So please pay attention to this step. The majority did it correct, but maybe because they did the homework independently, which is good. But please, the ones who confused here, do it carefully. Okay? Because in the exam, you will have at least 3 signals, not 2, like the quiz too, because of the time limit, you know. In the exam, you will have at least 3. So you will repeat this, you know, in more than a step. So please do it carefully, because you will have to sketch the 5 functions. And then you express the S's in terms of the 5 functions. If you have done the steps before correct, this will be correct, of course, you know. The S1 to this, so the projection, which the constellation is simply the projection, as you know, of the signals on the basis functions. So in terms of phi 1, how much is S1? How much is S2? What's the projection of, you know, phi 1, S1 on phi 1? What's the projection of S1 on phi 2, if there? S2 on phi 1. S2 on phi 2. Okay, if they are orthogonal, of course, like FSK, they will be separate, each phi, but usually they are not. In general, they are not. I'm not saying usually. In general, they are not. So they have projections like QBSK, projections in both sides, in both, you know, basis functions. For example, you know, QBSK has 2 basis functions, as you should know. So you will see such functions, please. You will be asked to do the GS procedure, as done here. So we did this example together. Please make sure about this step, as I told you, the graphical subtraction, you know, that you do it correctly to get the G, and from the G, if you get the G correct, you get the phi correct, because phi is a normalized version of G, isn't it? Yeah, please. And always double check your work before you write the final conclusions. And then you represent the signals in terms of the phi's. They can be on each phi, or they can be on the 2 phi's. You know, if you start at 45, then S1 will have projection on phi 1, and you'll have projection on phi 2.
دكتور I have a question.
Yes, go ahead, please.
عشان ارسم الرسمه اللي فوق هذه لازم اجيب البروجيكشن مثلا حق سيجنال 1 على phi 1 وعلى phi 2 صح؟
You express S in terms of the phi's.
Okay.
Yeah. Which are the projections by the end of the day, yes. So S4 equal, for example, S41 times phi 1. Okay?
Okay.
You express S in terms of the phi's, and then the weight is the projection. Example S41. This is S41. And S4 is expressed in terms of phi 1, yes. In terms of phi 1. You know, with a minus sign, because S41 is minus square root of 2. Okay? But it can be function of more than 1 phi, you know, in general. Okay? As I told you, in QBSK, for example. Depends on phi 1 and phi 2. And then we come to the detection. The general detection rule is the map rule. Please. You are at the receiver, you are observing X, the received signal. So given that we have observed X, what was the signal sent? That's the general rule. So map is the general rule. As I told one of you, map is the default. However, if the signals are equally probable, then map, the general case, will reduce to ML, the maximum likelihood, which some of you, they missed in the quiz before, quiz 4. What's the relation between map and ML? It's here. Simply, you know, ML is a special case of map. Map will reduce, or you say it the other way. Map will reduce to ML if the signals are equally probable. That's it. So the one talks about who wrote about the observation and observe. Okay, you can tell these things, but we are looking for a key. You know, in every question, there are keywords or key sentence. You have to state it. You want to state other details? That's okay. You want to describe map, as some of you they did, and then describe ML. I don't mind. But how do they relate? No, you have to tell me. But the key word here in the answer is equally probable. If you don't mention it, you will not get a full mark. Because that's the key word in the answer. All others are details, extra details, all other discussions. Map will reduce to ML only if the signals are equally probable. We know it math-wise, using the Bayes rule, isn't it? We express this probability, you know, probability of A given B, you can write it as in terms of probability of B given A, using the Bayes rule. Now, you can neglect the BIs, the fx, you can neglect it because it's not function of M. The BIs you can neglect only if they are equal. But if every M of the signals, the M signals, have its own probability, you cannot neglect BI. As I told one of you, if we are sending one of the signals 90% of the time, of course it will be more probable at the receiver. Don't tell me, no, we neglect BI. No, you cannot neglect BI. Assume mathematically, I mean, that one of them is sent 90% of the time. No, you cannot neglect. You can neglect the BIs only if they are equal. And that will reduce the map into ML. So you can rely on given MI, what's the probability of X, which we called it the likelihood. And then you take the log for the Gaussian. This is called posteriori probability. Given X, what's M? And given M, what's X, is called the likelihood, which leads to ML, the maximum likelihood. So please don't miss the key word in the answer or the key sentence.
For solving these questions, what do we need to find and what's usually given? Mathematically, not conceptually.
No, it's the definition and the relation. That's it. This is what you need to know about MAP and ML, which is this slide, you know.
So we do not need to solve them.
No. That's advanced, you know.
Oh, okay.
You know, in the graduate, we do. I ask them to apply the MAP derivations, but not in this course. You know, it will be difficult for you. Yeah.
Okay, thank you.
We know if you go into the graduate level, you will do it at the graduate. No, so conclusion, it's this slide. Clear? You know, you need to know this slide. This is the definition of MAP. It's based on X, observing X. It makes sense. You are the receiver. You are observing the received signal. What's MI? And it may reduce, for this case, to the observing only the likelihood function. And it's easier, by the way, mathematically, to obtain X given MI as compared to MI given X. Oh, because this will be Gaussian with a mean, which is MI for AWGN, at least for AWGN. So it's easier to deal with the max, even mathematically, to deal with the ML mathematically and graphically. It's easier to deal with the ML as compared to the MAP rule. And then the second part of the question. What is meant by the minimum distance detector? This is it. It's the detector or decoder which computes the Euclidean distances and chooses the minimum. the one which is nearest. Some of you wrote minimum, some choose nearest. Both are correct. You choose the nearest SXK to X. And this makes sense, you know. The nearest means the most probable, you know, means it's towards that region, within that region. This is what I'm looking for. You have to state that. You want to talk later about energy and this expanded form of this one. I don't mind. There's nothing wrong with this. But tell me first, what do we mean by the minimum distance decoder? It's the decoder which computes the Euclidean distances and then chooses the minimum. You have to state this. This is the key sentence. If you don't state it, you are roaming around the answer, but you are not telling it. So please, some of you, they jumped to E, they talked about probability. Already the probability is equal. Please don't go back to square zero or square one. We are already in the ML, dealing with ML. So why did you tell me about the probability being equal or non-equal? Please. And there is no need to talk about energy, you know, because energy is an expansion. If you expand this, the Euclidean distance, you will have energy there. There is nothing wrong with this, but it's not the answer. So please, in the exam, be specific. You want to add more details? That's okay, no harm. But the keywords need to be there. I think it's clear now. How does it look like? It's important to know how does the, you know, the receiver looks like, the block diagram. Okay, it implements, you know, these. It implements this one or implements this one in general. If they have equal energy, then it will reduce to this one, which is correlator only. Okay, so please read the question carefully. Are they equally probable? Are they equal energy? Or if it's not stated, assume. Okay.
Doctor, the minimum distance decoder or detector? Because here in the slides it's wrote decoder, and
I told you before
the
notion, you know, in here they are calling it, maybe you're not there, Reem. In here they are calling it detector, decoder, you know. Usually we use the notion of decoder when we have coding. So we should call this demodulator, and if we don't have coding, and we should call this detector, because, you know, here is done the detection, isn't the decision?
Yes.
Yeah. So formally,
what about the
decision,
detector
see?
circuit?
Decision. No decision is done here. So we shouldn't call it detector. The decision is done here. But it's, you know, in engineering, you know, we are not strict. It's not math, you know. It's okay. You know, assume coding is there. Usually they will tell you, usually coding is there. So we will call it the decoder. But strictly speaking, no, it should be called the detector. Because if we go to the notes of the coding, it's called formally the decoder. You know, encoder, decoder. We have started already. Remember the information theory? They are called encoder, decoder. They are, you know, they are additional to modulation. So formally, it shouldn't be include decoder. It should be called detector. And this one should be called demodulator.
Okay. So
But please, be pragmatic. Accept it. Yeah. Go ahead. Yes, sorry.
The distance is on the second circuit, which is here called decoder, right?
Yeah.
Okay.
maximum likelihood decoder.
Okay.
You know, this is the point. People from communication theory, they have their own terminology. People coming from information theory, they have their terminology. People coming from signal processing, they have their own terminology. And it will vary from one textbook to another, from one note to another, because all these guys are related, you know, to detection theory. All of them. I told you the course of detection theory is taught by signal processing group, not the communication group, for example. So you will see these different terms, you know. So information theory guys and coding guys, you know, like Dr. Alim Gable and others, they prefer decoder. We communication theory guys, we call it detector rather than decoder, unless coding is there, along with modulation. But here is modulation only. Clear now? Clear,
Yes,
yeah?
thank you. Yeah,
Good.
thank you.
Perfect. It implements this one. You know, the decoder. You know, let us call it decoder. I agree with them. So it computes the inner product, which is this one. You know, and then it subtract the energy if they are not equal energy. Now, if they are equal energy, do we need this step? Do we need it? They are equal energy. No, redundant, because all the M's will have the same, you know, E. So it's like DC value for all of them. We will select the largest based on the inner product. Okay.
Doctor, when they are not equal in energy, the largest energy.
We have to include this. We have to include
Yeah, the largest energy, does it imply it's the minimum distance?
it will subtract, you know, from here.
Yeah, so in conclusion, the largest distance is the maximum, the minimum.
Yeah, think about it. Think about it. The higher the energy, what will happen for the signal in the signal constellation? What will happen for the signal? The intuition behind it. Mathematically, it's coming from here, of course. The expansion, you know, of the Euclidean distance. Well, if you
Yes.
expand the expression. But physically, remember, signals are represented as vectors. The more the energy, the lengthier the vector, isn't?
Yes.
So it will be far away, isn't?
Okay.
Yeah, from the others, isn't?
Yes.
Yeah, that's the point. This is the term it comes to interpretation. But usually we avoid that, by the way, in practice. You know, the signals are similar energy. Now, so this one is implementation of this one. Now we come to this one. Remind me. You have to do both. And, by the way, in other textbooks, it's one diagram. You merge this with this, you link them. What are we doing here and why? Tell me, just to make sure that you are following.
It's the correlator, the match filter.
This is the correlator. It can be implemented also as the match filter. You know, yeah, so you can do it either this way and this way. So this is number one, okay? Number two, using the basis functions, of course. Why do we do it?
So we can increase the SNR.
And then what will be the output? What will be the output? Numbers,
Is it the
is it?
projection?
The projections, exactly. And we call that the observation factor. Now, what do we do with the observation factor? Now here, what do? We have to know the logic behind this. You know, not memorize it as a diagram. We have to know it. what are we doing with the observation vector here, which contains the projections on the basis functions? What do we do with it?
Inner product with the signals.
Yeah, mathematically, but physically, what are we doing? We are checking the similarity of that observation vector with what? The inner product is similarity, please. With what? With all the possible
Signals.
yeah, S1 up to SM. So the transmitter and the receiver, please follow this carefully. They are sharing the same signal constellation. They know it, QBSK, for example. So what the receiver will do, project the received signal on the basis function, will have an observation vector. And then the signals are already represented as vectors in the constellation. It will compute the inner product of this vector with each of S as a vector. There is no T here. If you write S1 of T here, you are doing a conceptual mistake. Yeah, it's not numerical, it's conceptual. Because you are telling me you will compute the inner product of a discrete vector here after computing the projections with a time domain signal. How come? No, we compute the inner product of the observation vector with the S's as in the constellation, S's as vectors, which we obtained using the GS procedure. If you think about the GS procedure, it took us from which domain to which domain? The GS. From which representation, I would say, to which representation? Tell me.
Vectors.
No, we start with what? In the
Time domain.
GS procedure. What time domain? And we end up with the signals represented
As
as
vector.
that's it. So these are the vectors used here. Please, you have to link things. This is very important. Because what we have done before is for a purpose. That purpose will reflect in the detection, or call it decoding, or decision, whatever you call it. Huh? Call it decision device, or circuit. Yeah, it's the same. This is what we are doing. This is DC volume. It can be different DCs or same DC volume. But this one is a mathematical operation. You have to know why. You have to know the physical interpretation of that operation. Clear, please. So the distinction between time domain in here and vector domain in here is clear, very clear. And then we select the largest, please. This makes sense because inner product is measure of similarity. The more the similarity, the more the probability that it will be that signal being sent. Unless the noise has deceived the receiver. And you can do nothing for that. Okay? You can improve the performance using coding, which we will study soon. Yeah, but you cannot eliminate the effect of the noise. You can reduce it, but not eliminate it. Usually we implement using the correlator, by the way. But remember, mathematically, it's equivalent to the match filter at t equal to t, uppercase. And, this is for your information, rotation and translation do not change the bit error rate expressions. And this makes sense. Think about QBSK. If you, or PSK in general, or QAM. If you rotate it, then you are rotating the decision regions, all the decision regions. So it won't make difference, you know. Yeah. This is, there is a mathematical proof for it, but we will not go into that. Now, before I forget, the decision regions, please, are important, you know, and they are based on the assumption of equal probability, which usually we do most of the time, you know. Again, read the question carefully. So the default is equally probable, by the way, in quizzes and exams, unless you are told otherwise. So the number of decision regions equal the number of signals we have. It makes sense. And if they are equally probable, we know the rule. We connect the 2 points. I sent you even from another textbook on the teams in general. Even if the shape is irregular, you can obtain the decision regions. Yes, it's more difficult than here, but it's doable. Anyhow, you connect the 2 adjacent points by a line, and then you draw perpendicular at the center of that line, connecting the 2 points, please. If you do that, خلاص, by symmetry, you see the decision regions. Okay? Yeah. But try to do that example after the exam, huh? By yourself, the one from the external source. Huh? It's interesting. Yeah. I took it from the graduate course, you know. I'm bringing some notes and stuff from the graduate. The course, the textbook we use for the graduate course, for your understanding, please. Huh? Yeah, remember, we don't do everything for quiz and exam. We go beyond the quiz and exam. But when it comes to quiz and exam, things are well defined. Please, as I told one of you today, in detection or decision making, it's not a matter of equality, the math-wise. No, it's a matter of which terms you care about. You always consider the terms containing M, because you want to decide which M. If a term like is common, like this one, you drop it from the this. When the BIs are the same, we drop them. So we are left with the likelihood function. Okay, this is the way we do detection. We call it equivalency, please. In note here, you may drop it, you may bring it. Free. It's okay. In note is the same for all the signals. It's not function of M, so it will not make difference in the decision. Because the decision will be chosen a certain M. If a parameter is not function of M, will it make difference? No. It's either DC value or scaling. Here it's a scaling. You scale by the same number. Or for equal energy, it's a DC value. You are using the same value, so it will not make difference. The noise is always the same, but the energy can be different. Please. So in general, in the detector, I think I received a question about this. You should include the energy term, unless you are told they are equal energy. Yeah. For consistency, okay? Please. I'll accept it if you tell me if they are equal energy, then the energy is not there. But being silent about it, no, please. Being silent about probability, I accept it, because halas, it's by default equally probable. But energy, no. Energy has to do with ML. If you expand the Euclidean distance, you get the energy there. So you have to say something about energy when it comes to ML. Okay? The safer way is to include it. Why not? Sorry. Done. This is for the first part, and then we come to the second part. Now again, RIM or RIMA, if you use detector, the question is, where is the demodulator? We have modulator here. Where is the demodulator? So formally, it should be called the demodulator, by the way. Yeah. And then you have this, call it detector, call it decoder, call it decision device, whatever you like. But there has to be a demodulator. This is what I mean. Whatever we do in the transmitter, we reverse. But since he's using encoding here and decoding here, they start with a message. This is the notion of information theory. Huh? I mean, information theory guys, they show communication system this way. In communication, no, we call it, what do we call this one in communication? What do we call it?
Signal.
Yeah, transmitted signal. Yeah. So, but it shouldn't be a big deal, you know. It's a matter of convention, as I told you. This is similar to, you know, I received a question about QBSK and BBSK. Why they use square root of EB? It's again a matter of convention. You can use square root of ES. But in order to compare, you know, fair comparison between QBSK and PBSK, they use square root of EB for both. You know, it's a matter of convention. There is nothing wrong with using square root of S, which is 2EB for QBSK. Formally, by the way, it should be square root of ES. But there's nothing wrong with scaling it. So we have the M array, M binary and M array modulation schemes. You know these basic relations: M equal 2 to the power K, please, not N, and T equal NTB, where T here is TS, please, by default. Huh? You know, this has to do with the question, you know, is this required? No, please. I received a question. In general, for your understanding, but quiz and exam, not required. For your understanding, it is. Because you will see discussion about the BSD, and most of you are in the concentration in 419, you know. So I want you to be aware of the BSD, you know, at least the definition, you know, that the different modulation schemes, they have, you know, different BSDs, yeah, and it has to do with the SAF magnitude of H square, you know, these things. I want you to be aware of it. Bandwidth efficiency is very important. You know, we are doing this. By the end of the day, we are doing engineering course. We have outcomes. We are doing a math to compare, you know, the mathematical representation of modulation schemes and to compare them by the end of the day. So one of the important, you know, metrics is the efficiency, the bandwidth efficiency, which is defined as RP over B. Please, you have to know it. Don't tell me I provide this formula, please. For example, formulas for the GS procedure, of course, will be provided. You have to know how to do the procedure. Formulas will be given. But simple concepts like this one, how much rate can we transmit for a given bandwidth? Please, you should know it by definition. The family is the BSK family are bandwidth efficient. So when you compare PBSK and QBSK, you know, in terms of basis functions, PBSK has how many basis functions? How many? How many? One. No, PBSK has one. One and minus. You know, it's cosine and minus, isn't it? You have 2 points only, square root of EB and minus square root of EB. So how many dimensions you have? The one who said 2. Why 2? It's only one, PBSK. QBSK has how many basis functions? How many dimensions?
2.
Basis functions is the number of dimensions, please. How many QBSK?
2.
2. Which one is more spectrally efficient?
QPSK.
Of course, because M is higher. So it's here, you know, QBSK, you know, it's higher spectral efficiency than PBSK. Even from E370, you are sending 2 bits per symbol. How come you tell it's the same as sending 1 bit per symbol, which is PBSK? So this can be answered by intuition, the one who confused there. Please be alert. You are an engineer. You have to think. Even if you haven't seen this table, you should be able to answer it from E370. Why do we increase M? To increase the rate. just for the same bandwidth. Please. Now, from our course, you know it. It's log 2m, isn't it? We know the higher the m, the more the spectral efficiency. The beer, they have the same beer. Why? Because QBSK can be represented as, I'm answering the quiz, huh? Can be implemented as two arms, you know, of PBSK. Yeah, so PBSK has one. The one who said two. No, only one basis function. Because y will reflect as -1. So we don't need another basis function. So it has only one basis function. Please, you have to know this just like your name. This is the core of the course. Course is the modulation schemes. Others are important, not as important as the modulation schemes. And QBSK has two, clearly, you know. So this is BBSK. It's one-dimensional. So it's one basis function. You know, you don't need to do math even. Think about the representation, square root of EB and minus square root of EB. That's one-dimensional. You know, and you should be able to handle the I received a question about this. The derivations for binary. You should be able to do the derivations for PBSK, which is, you should be able to do them. You'll be given the Gaussian BDF. But you will not be told that it's square root of EB plus, minus the mean, you know? So it becomes plus. No, you should know that from E315. And you should know how to do little, you know, change of variable. That's all what you need to know.
Doctor, can we derive it by using the distance formula directly?
It depends on the statement of the question.
Okay, how to do it in other way?
Other way is a piece of cake. You know, you have the distance as square root of 2EB. Khalas. You square it for EB over 2 N naught, Q of 2EB over N naught. That's a piece of cake. I'm talking about this one. This is more involved because it requires some calculus skills. Huh? Not much. It's only this step. This says, you know, it's the area under the curve in the other region. And the threshold is at 0. We are assuming equally probable. So from 0 to infinity. The Gaussian BDF centered at minus square root of EB. Because you are sending 0, so the error will be due to being at the region of 1, isn't it? As you know. So then you do change of variable small, you get the expression. You will be given the Gaussian BDF. You will be given the definition of the error function. So only you need to know this step. It's challenging? No. Please, you have to have some, acquire some, please. You want to get an A+ or A and you don't have analytical skills? How come? Please, no. You have to have some analytical skills. It's a must. Otherwise, this grade is overrated. You know, it's superficial. It's not real. You know, I'm not saying the MRA. The MRA, I didn't ask you to do it. It's involved. Yeah, I know. Even for our graduate students. But I asked them to follow it. You know, in the assignments, I asked them to do something similar. But even in the exams, no, I don't ask them for it. It will consume the exam time easily. But they should know it. For you, no, you need to know the binary only. So you have to be ready conclusion for both. You know, the integral approach or the distance approach. And they will lead to the same answer, of course. Now, QBSK has two basis functions, please. And in general, MBSK and QAM, they have two basis functions. That's well known. The bit error rate for QBSK, I explained here. I did it a different way in my notes. It's for your information, you know. I want you to know about how we do it, but you are not assumed to redo it in a quiz or exam, please. But you should know the concepts, you know, the independence, the two arms of PP is K, you know, in the interpretation of QB is K. This one, you have to know it. Agreed. You should be able to apply it. And you have to be able to calculate the distances, please. It's your responsibility. Or to use geometry, you know. It's basic math, you know. Trigonometry and algebra, and, you know, should be able to calculate the distances. That's a general math. Has nothing to do with E417, please. It has to do
This
with
formula will be given.
yeah. This formula will be given.
Okay.
I'll give it most probably in terms of the Q function. It's okay.
Yeah.
F or Q, you know, they are the same. You know, they are scaled versions of each other. And the M array, you know it. And then the QB is K. You know, if you want to know this distance, you know, the distance for it's explained in my notes, huh? The sign, you know, how do we get this? I'll not ask you, but for your information. Remember, no derivations for M array. M array just applying knowing the constellation. The announcement is very important, please. I did before. Knowing the time domain representation. You know, this one. Knowing the constellation, which is straightforward. And knowing how to apply the bound, which depends on your skill in calculating the decay, the distances, which has to do with your math skills, please. So yes, the M array, the MBSK family row is log 2M. So how come QBSK and BBSK have the same? No, they cannot. One has M equal to 2, one has M equal to 4. So they don't have the same spectral efficiency. Please. It should be clear. And you go anywhere, everywhere. Of course, they are different. This is scaled by 2, huh? It's scaled by, because we divide by 2. You know? So they are different. They are not the same. How come? You contradict the math? Please wake up. Log 2M over 2. And remember, in a proportional to M. That's it. You don't have to remember log 2 over 2. Although it's easy to remember, but you have to. And then the QAM, you know, we know the merit of the second question, please, in the quiz. What's the merit of QAM? It's the more distance. D-min is larger as M increases. That's it. That's the benefit of QAM over PSK. Oh. So it's 6, my derivations, you remember, for ASK and BSK, and it's 3 for QAM. So QAM, you know, is more efficient, energy efficient. So key answer is energy efficiency. That's it. You know, and that's it for the.
Doctor?
We stop here for the. And now I listen to your questions, please, about, you know, the material. If you have questions, let me stop sharing. Yes, go ahead, Rima.
Doctor, for the bound equations, we need to know 3 equations, right? Can we have an example for the 2 equations in your notes? Yani it's a little bit confusing.
No. There is no confusion at all. They are special cases. Let me go back. The general one is this one. You know, the I don't see, please, it comes to math now. Please, the mathematical skills are very important in communication systems. This is the general expression. Are we sharing?
Yeah.
Now, if the DIK are the same, what will happen for this summation? You are summing the same quantity, M minus 1 times. So you end up with that
Multiplying.
quantity times M minus 1, isn't it?
Yes.
Clear? That's the second one. So the second one assumes the DIK are the same. Depends on the constellation you are given. They can be the same or similar. They can be different. So you have to look at the constellation given. Clear? Yeah. Number 2, the n minimum. The n minimum, you have m minus 1. Assume they have similar distances. So you replace the summation by m minus 1. It is. Now you want to consider the adjacent ones only. So we call it n minimum. Or call it m minimum if you like. You know, but because m is fixed, the number of signals. So we call it different symbol, n minimum. N coming from neighboring. Huh? The minimum number of neighboring signals, which is 2 or 3. So it's a special case of this one. You are neglecting the signals which are far away, the decision regions which are far away. You are considering the adjacent decision regions. That's it.
Okay, so if we are considering
So they
it,
are bounds 2 and 3 are special cases of this one, simply. Yeah, they are limiting it. He's using it here. You know, now he's considering 2 only, for example, rather than 3. So he's reducing adjacent only. You know, he's using it also for QAM here. You know, taking when he applied the bound, you see in here, they ended up with 2, I think somewhere, yeah. They applied it for QBSK. For QAM, it's approximate. It's from the expression I've shown you for the MQAM, the general, which we do. But it can be applied. It will lead to, if you consider the 2 adjacent only, it will lead the same. But it's clear here for QBSK, where he considered only 2 terms. Because for QBSK, tell me, how many terms should be there for QBSK in general? How many in the summation?
2.
How many? QBSK, m equal to?
4.
M minus 1 equal to?
3, okay.
3. It's decision regions. Please wake up. You have 4 decision regions. So you are here. You have to consider the error due to being here or being here, which are the adjacent, or being here. 3. He did 2. And he said M3 can be ignored at highest NR. It's a special case, but formally, it's 4. Clear now?
Yeah, doctor, what about in minimum? It's for the adjacent.
In minimum, when you have higher, like 8 BSK, you consider only the adjacent 2. Clear?
Okay, only 2, يعني it's usually 2.
Yeah. Only the adjacent, the 2 adjacent, you know, he did it here. You may consider only these 2. He did it. So how many terms we had?
2.
2. So we consider these 2. So that's n minimum. So it's a special case, you know, this one.
A special case for BSK, right? Not QAM. QAM has another
No.
equations.
It's how many terms you consider in the summation, Rima. Yeah, that's the question. You want to include all of them, or you include some of them based on a criteria. If you include all of them, well, that's the general case. If you include some of them, you are considering the adjacent only, as he has done here. That's it. So, is it clear now?
Yeah, clear. Thank you.
Yeah, it depends on how many terms you want to include in the summation. Of course, the more terms you include, the more accurate. Of course, we call it the more tight. is the bound. There is no doubt. But in engineering, you know, sometimes, tell me now, with MBSK, with M equal to 8, how many terms we will have here? Formally, how many?
8,
No, not 8.
7.
It's M minus 1. Remember, you are at a certain region. You are correct with yourself. So the error is with others, isn't it?
Yeah, right.
So how many k does not equal to I? Please, physically and mathematically. If you are at the same region,
7.
it's correct. 7. You know, engineers, they don't like, you know, tedious, they call them tedious expressions, you know. No. Why should I include 7 terms? We want nice expressions to end up with nice conclusions. You know, so let us include the 2, the adjacent 2, and then we lump it into 1 term in order to compare it to the binary. See the point? In engineering, we like simple expressions. Why? Because they lead to what we call it in engineering insights. If you have 7 expressions, you know, 7 terms, I mean, what insight you would draw? No. Numerically, it's good. But when it comes to insights and conclusions, no, it's not good to have too many terms. But with 2 terms, you lump them into 1 term. No, with approximations and these things, you lead to expression which is insightful. Because you want to compare, remember, to the binary case, which has 1 term. You remember Erfkov, 1/2 Erfkov, EB over 2 N naught, the one for PBSK. So this is what they have in mind. So it depends. You want to end up with, which is here, you know, QBSK or PBSK, you know.
Doctor?
It's here. Yeah. So it depends. Are we targeting, you know, numerical accuracy, or we want to compare to the basic, you know, binary? If we want to compare to the basic binary, we have to reduce things as much as we can into 1 term in order to compare 1 term to 1 term, which he did here for 8BSK, you know. But if you want, you know, it's approximate, of course. If you want numerical accuracy, of course you will not go with this. No, this is unacceptable. You are dropping terms. You have dropped already 5 or 6 terms. 5 terms you dropped. No. So it depends on what you are
Doctor, I have a
targeting.
question.
Yeah, go ahead.
If we want to use the N minimum bound for the QAM, how would we choose the N?
That's 2, these 2.
No, for the QAM, not PSK.
And here,
Yes.
so you have to make a grid of the decision regions. Okay. It's similar to QBSK, I would say, if you consider this. It depends on how many you want to consider, you know, but you would start with 2. And if you want, you may consider this one to end up with 3. You may consider these 2 to end up with 5. If you are here. If you are here, you would consider these 2, isn't it?
Yes. But
so in general, it's I told you, it depends. If you want to end up with an expression compared to the binary, you would take 2. And then you combine into a single expression. If you are targeting a numerical accuracy, no, then you have to include as much as possible. So I would say the rule of thumb for N minimum is 2. Yeah. But remember, it's not to calculate the probability of error. because it will be a rough approximation. It's to compare to the binary case. See, daemon, you go with daemon. You will not go here. Whatever points are at daemon, you have to consider them. So they are these two. This is QAM, 16 QAM. Maybe you consider this one maximum, but not these. If you want to consider all of them, you program it into MATLAB. You program that expression, you program daemon in MATLAB, and then you do it in an M file. Okay? But remember, in QAM, rectangular QAM, we had an expression exact from the combination of two the derivations. I've shown you my derivations of 2A BAM. So we have a good expression there. It's not like BSK. Remember, 8BSK, we don't have a closed form expression for the, as I've shown in my notes also. Go back to my notes. There is no closed form expression. So using the bound is a must. For QAM, using the bound is an option, but you have an exact expression. You can simplify it, You see the point, Rima?
Yes.
Yeah, so it depends. For certain modulation schemes, you have the exact expression, or almost exact, very approximate, like QAM, especially rectangular QAM. And you can approximate for non-rectangular QAM. But QBSK, we don't have the expression. There is no, sorry, 8BSK. QBSK we have. 8BSK and more, we don't have the expression to start with. So using the bound is a must. Yeah. It's not an option. Clear?
Yes, thank you.
Okay. Other questions, please proceed. Now I listen to your questions. I'm done with the explanation of the material. This is preparation for the final, by the way. You're implicitly preparing for the final. Please feel free to ask questions,
دكتور
whatever questions you have. Yes, go ahead.
في اللي هي النوتات حقتك، هل هي تعتبر من ضمن الماتيريال حقت الميجر؟
No, except for the daemon. We agreed on this. The daemon, which is, by the way, it's the DIK. Daemon square. That's the only one.
يعني
Because binary, binary, it's not daemon, it's D12, by the way, because it's binary. خلاص, the daemon there is no daemon in binary. They have 2 points only. So you have one distance only. We call it D12. So it's the square root of D12, square root of D12 square over 2 in note Q of, that's it. If you forget it in the exam, I'll help you with it. I care about being able to apply it, for a certain constellation. Binary constellation, of course. Muhammad, why you are on hold? Muhammad, you have difficulty? Muhammad, you are... okay. Just in case. Yes, please. Other questions?
يعني يا
دكتور
دكتور
ديمين
Yes, go ahead, Faisal.
ديمين في ذا كوام.
Let us finish Muad with Faisal. One second. Yes, Faisal.
لا نفس السؤال معاذ دكتور ما
Yeah, go ahead Muad. Yeah.
دكتور الديم اللي قلتها بخصوص اكوام ولا اي؟
لا دي مني يا شباب for any constellation الله يحفظكم. Any constellation. It has some demon, yeah. Let us say it this way. If there is demon for the point. Some constellations, they are symmetric, huh? They have the same D-min. You know, some constellations may have signal points away from more than D-min, but we care about D-min. Please, in binary, again, there is nothing called D-min in binary. In binary, there is D12. So let us clarify this. Now we come to M-array. D-min. Why we care about D-min? Whether the constellation is symmetric or asymmetric in general. Why do we care about D-min?
لأن الإيرور بصير يعني أكثر عندها غالبا بيجي عندها.
Exactly. The error will be related to D-min. You know, most probably, you know, the noise voltage will affect the signals which are at D-min from each other, the minimum distance. Why should a signal which is far away in QAM, for example, be affected or confused, namely, with the other one? It's there's no zero probability, but there is, remember, it's Gaussian from minus infinity to infinity, but there's a very almost negligible probability, okay, that it will affect that signal point which is far away. So yes, D-min makes sense whether the constellation is symmetric or non-symmetric. Yeah, this is the reason why D-min, you know, frequently appears, you know, in bit error rate approximations. SEER approximations, not bit error rates. Bit error rate, we know it. There's no need for approximations. We know the exact expressions. Clear, معاذ؟
يعني دكتور مطلوب مننا نعرف كيف
ما في دي، ما انا ما طالب دي من دي اي كي تحتاج تعرف، بس انا اقول لكم دي من conceptually انها مهمه يعني. بس طبعا في expressions they have to do with d min and these things, but we are not going into these details. We don't have time for that. But I wanted you to be aware of this. You know, d min is very important.
يعني هي بس الأكوام فقط، يعني الباوند اللي نحتاج نعرفه.
مش الكوام، البي اس كي يا شيخ، مش الكوام. الباوند is usually used for M-array BSK. in الكوام عندنا almost exact expression.
حتى M-array كوام
هي موجود. The notes I've shown you before, see it, you know, about QAM. We discussed together. I've shown you the derivations about QAM. Yeah. QAM, we have closed form expressions. MBSK, we don't have closed form expressions. Yeah. My notes, Shabab, for my graduate course, they are there on the blackboard. If you want, for your knowledge, you can go and see them, please. I discussed in the class quickly.
دكتور بالنوتس ما في باوند لل M-array-BSK.
How come? The one we have seen in a minute, they took 2 for MSK and they took 2 for QBSK. We discussed in a minute.
أنا فاتح النوتس ما في باوند له، في final expression.
Don't confuse yourself, please. What's this? Here is the bound.
لا أتكلم بالنوت.
No, and not the bound I mentioned at the end in terms of D-min اللي هو D-min M-1 and on these things. You know, you mean that?
إيه نعم اللي بالنوت.
Notes are about, my notes are about the exact expressions mainly. The target is the exact expressions. Because this is the way we do it at the graduate level. We struggle for the graduate course for the exact expressions as much as we can. And then if we are stuck with them, we resort to the bounds. This is the way we do it, but not in here. In here, we didn't go to the exact expressions for MRA. We went directly to the bound, is that?
صحيح.
Clear? Yeah, this is the difference, you know. So it's the approach being used, you know. Yeah.
ودكتور خصوصا الاماري ASK هل هي معنا ولا لا؟ عشان ما هي موجودة بالسلايدات.
No. You know, MRA, ASK is similar to BAM, you know. So yeah, the derivations for MRA BAM are not included. So hence for ASK, they are not included, the MRA. But the binary, please, you should know it. For example, on-off keying. Huh? Now, did you study on-off keying in the optical course? Don't tell me you haven't seen it. Did you see it? Did you see it in the optical course?
We see it, but not that much details. Maybe only one slide.
It's used. This is what I'm saying. You know, that's the ASK usually. We consider Mu'ad, okay? Yeah. I'll stop recording here, but I'll keep, you know, listening to your questions.